Welcome students, welcome for the today's session of ALPHORES e-learning program. Let us continue with the expansions of solids applications. In the previous class, we have studied some applications regarding the expansion of railway tracks. We have studied two conditions there. Let us have a brief recap of those 2 points and then we will continue. When we are having the applications of railway tracks, we have given that the gap to be left between the two rails. Suppose these are the two rails. Let the expansion of the first rail is delta L1 and the expansion of the second rail, let it be delta L2. Then the gap to be left, let us say the gap equal to, it is equal to the average expansion of the two rails, that is delta L1 plus delta L2 by 2. This is the average expansion, that much of gap is to be left. But in general, if all the rails are having same length because they are made up of same material, delta L1, delta L2 may be the same. Then the gap will be simply equal to delta L, which corresponds to expansion of each rail. So that is one application. And next one, when the total length length of the track is given, suppose there are two stations A and B. Between the two stations, if the distance is x, then to get the sum of all the gaps present between the two stations, then simply consider that there is a single rail of length x and find out the expansion of this single rail whose length is equal to distance between the two stations, and that gives the sum of all the gaps. So you can say the total gap to be left equal to x into alpha into delta t. So this is an application we have completed in the previous class. And just for a recap, I have explained that. Now let us come back for today's class. Let us continue with some more applications of expansions of solids. Suppose, first let us consider the case of a body. I have taken a cylindrical body of, let us say, radius is r and length is l. And suppose it is made up of iron. It is made up of iron. So it is an iron cylinder of length L, radius is R. Let us say it is like this. Now this is a solid cylinder in the form of a rod. And let us consider another cylinder of same length and made up of iron only. So this is also made up of iron, having the same length and having the same radius. Then when the thickness is negligible small, corresponding to length, if you observe the linear expansion, what we have studied is delta L, linear expansion, delta L equal to L alpha delta t. The linear expansion or an expansion of length that is given by L alpha delta t. Here L is the length, alpha is coefficient of expansion, which is the property of the material, and delta t, that is the change in temperature. But now for both the bodies, suppose there is an equal increase of temperature delta t. But remember, this is a solid iron cylinder, this is a hollow cylinder which is empty inside. Very clearly, because this is empty, the mass is less, and because it is a solid body, mass is more. But if the change in temperature for both of them is same, that means change in temperature for solid body and the hollow body both are one and the same. Then because initial length is same, because both are made up of the same material, alpha is also the same. As a result, delta L will also be the same. So delta L will be the same for both the rods because they are made up of same length, same material, and they are having the same initial length. But remember, when change in temperature is same, suppose the temperature we don't know about that, and I have supplied same amount of heat, let us say equal to Q, that is supplied to both of them. When same amount of heat is supplied, change in temperature for both of them will not be the same, because whenever we are supplying heat to a body of mass m, then the change in temperature we can calculate from the equation. Heat energy given to the body is ms delta T, where m is the mass of the body, S is known as specific heat, which is again a property of the material, and delta T is change in temperature. Now, if you observe, both are made up of the same iron, so specific heat factor is same for both of them. Specific heat is same for both of them, but very clearly here, when you supply same amount of heat energy, MST is a constant, MS delta T is a constant, but already yes, the specific heat, it is same for both the rods, because specific heat is also the property of material. Both are made up of iron, so S value is the same. So very clearly, because this is a constant for both the rods, M into T should also be a constant. When M into T is also constant, because it is a solid body, mass is large, so change in temperature is small for this one. And here let us say delta T it is. Delta T is because of smaller mass, delta T is more for this hollow body. So in such case what happens? Corresponding to the larger mass, delta T is small, and here delta T is more. So using this equation, having the same initial length, delta L equal to L alpha delta T is more in case of this hollow body. So expansion of this hollow cylinder is more than expansion of the solid body. So here, because of the larger mass of this solid cylinder, change in temperature is less. As change in temperature is less, it will expand only by a small amount, but corresponding to the same amount of heat energy supplied, because of the smaller mass of this hollow cylinder, there will be large change in temperature. As a result, expansion of this hollow cylinder is more. So very clearly remember that in cases when equal amount of energy is supplied, when both are having the same initial length, remember that hollow body will always be having a larger expansion than the solid body. You can consider this as a standard result. Even you apply the same thing for, suppose there is a hollow sphere and a solid sphere made up of same material. Similarly, the solid sphere will have a larger mass. Corresponding to that, change in temperature is small. So, the solid body will expand by small amount and hollow body will expand by larger amount. So, you can remember this point as an important standard result. When physical dimensions are same, when same heat energy is supplied, the hollow body will always expand more than the solid body. This is a standard result. Now let us move on to another application. Suppose I have taken a rod of length L1. It is made up of a material whose coefficient of linear expansion is alpha 1. Now I will take another rod of length L2 made up of another material of coefficient of linear expansion alpha 2. For both of them, the change in temperature, let it be the same. Change in temperature delta T here and here also delta T. Now let us say that the difference between their length, let us suppose L1 is greater than L2, so that the difference between their length, let us say it is x. The difference between the lengths of the two rods, let it be x, and I want it to be a constant at all temperatures. Initially, let us say we are taking both the rods at a temperature T1 degree centigrade. The first rod, let us say the rod is A, this rod is B, made up of different materials, but both are initially at the same temperature T1 degree centigrade. And length of the first rod is more than the second rod, so that the difference between them is x. Let us suppose have a numerical example. First one is having a length 11 centimeter, second one is having a length 10 centimeter. The difference is L1 minus L2, 1 centimeter. Now, I want to derive a condition that the difference between their lengths, that is L1 minus L2, which is x. In the numerical example we have studied, it is 1 centimeter. I want it to remain as a constant at all temperatures. whatever may be the change in temperature, I want this difference between their length to be a constant. Then what is the required condition for that? To get the required condition, let us suppose we said initially the first rod is having a length 11 centimeter and this is having a length 10 centimeter, so that the difference between their length is 1 centimeter, which we want to make a constant. Now suppose because of increase in temperature, this rod expands to a value 11.5 centimeter. So expansion is 0.5 centimeter. Now to have the same difference of 1 centimeter, this must be expanded by 0.5 centimeter, so that the final length of this rod will be 10.5. Now let us see the difference. This is expanding by 0.5 centimeter. This is also expanding by 0.5 centimeter. And now the difference, if you take between their lengths, again 11.5 minus 10.5, it is only 1 centimeter remaining constant. That means if the difference between their lengths, that is L1 minus L2 x, should remain as a constant, the required condition is, what is change in length here? 0.5 centimeter. Here also it is 0.5 centimeter. That means their expansions must be equal. Their expansions must be equal. That is, delta L1 must be equal to delta L2. If the expansions of the two rods are equal, then only the difference in their lengths can be maintained as a constant. So to get the condition, let us use this point. To have a constant difference of length at all temperatures, they must have equal expansion. They must have equal expansion. Now let us apply this. Delta L1 equal to delta L2. Now delta L1 is the expansion in the first rod. It is delta L2 in the second rod, but both are equal here. So using the equation for delta L, it is L1 alpha 1 delta T, that equal to in the second rod, L2 is initial length, coefficient of linear expansion alpha 2 into delta T. That means L1 alpha 1 delta T equal to L2 alpha 2 delta T. Now very clearly the necessary condition is L1 alpha 1 equal to L2 alpha 2. This is the necessary condition for the expansions of the two rods to be the same. But when the expansions of the two rods are equal, difference between their length is also remaining as a constant. So necessary condition, we can use this equation. When this condition is satisfied, their expansions are equal. As a result, difference between their lengths is also a constant. So L1 alpha 1 is L2 alpha 2. Now we have taken initially that L1 minus L2, that is the distance between the difference between the two lengths, let us say x. Now I want the values of L1 and L2 to so that they will satisfy this condition. So you can write that L1 by L2 from this equation, L1 by L2, it is nothing but alpha 2 by alpha 1. Now let us subtract 1 from each side. That is L1 by L2 minus 1, that will be equal to alpha 2 by alpha 1 minus 1. Taking LCM, you will get the result L1 minus L2 by L2, that is alpha 2 minus alpha 1 by alpha 1. Now L1 minus L2, it is a factor which we wanted to maintain as a constant. That is the difference between their lengths. We have said it is nothing but x. So using this relation, what we can write is L1 minus L2 is x. So x by L2, that will be equal to alpha 2 minus alpha 1 divided by alpha 1. Or if you want the value of L2, you can cross multiply x of alpha 1 by alpha 2 minus alpha 1. You will get the value of the length of the second one, so that this condition is satisfied. So L2 you can get like this. Similarly, taking L2 by L1, that is equal to alpha 1 by alpha 2, and substituting here, you can write also like L1 equal to x of alpha 2 divided by alpha 2 minus alpha 1. So we can use these two equations to get the values of lengths of the two rods, so that their difference between their lengths remains as a constant at all temperatures. So this condition we have to remember. and here very clearly L into alpha is constant. That means when alpha is larger, length of the material, length of that particular material, rod made of that material is less. So that this product is a constant. So a material of larger value of alpha will have a smaller length, and a material of smaller value of alpha should have a larger length, so that this condition is satisfied. So from this L1 and L2 we can find out values of these two factors. We can use these two equations. And necessary condition is L1 alpha 1 equal to L2 alpha 2. So this is the necessary condition for equal expansion in length, and also to maintain a constant difference in their lengths at all temperatures. Similarly, taking this condition L1 alpha 1 equal to L2 alpha 2 for equal linear expansion, to have, let us say, equal areal expansion we want. To have equal areal expansion, let us say delta A1 equal to delta A2. Then you will have A1 beta 1 into delta T equal to A2 beta 2 delta T. Then the areal expansion is same. Then you can write A1 beta 1 equal to A2 beta 2. This gives a condition for equal expansion of area. L1 alpha 1 equal to L2 alpha 2 is the condition for equal expansion in length, and this is the condition for equal expansion in area. And similarly, if you consider in a volume expansion, to have equal volume expansion for two bodies, let us say delta V1 equal to delta V2. So V1 is, delta V1 is V1 gamma 1 delta T, and delta V2 is V2 gamma 2 delta T. We are taking two different bodies of different volumes. Change in temperature is the same. Then very clearly V1 gamma 1 equal to V2 gamma 2. This is the necessary condition to have equal volume expansion. So all these three conditions are definitely useful to get for when we are solving the numericals related to these expansions. L1 alpha 1 equal to L2 alpha 2 for equal linear expansion. A1 beta 1 equal to A2 beta 2 for equal expansion of area. V1 gamma 1 equal to V2 gamma 2 for equal expansion in volume. All these conditions are very much important. Now, let us move on to one more application which we come across in our daily life. When we consider a circular ring like this, circular ring, when we are increasing the temperature, we said it will expand. What will expand here? The radius will expand. As a result, the circumference will also expand. But when the radius is expanding, because the expansion is radially outwards, the expansion, or if R is the, let us say R1 is the initial radius, because of change in temperature, there will be an increase in the radius. Let us say delta R is the change in radius. You can say initial radius R1 alpha delta T. That means this will be expanding such that the radius is like the length. That means this distance will be increasing just like the expansion of length. That means delta R you can calculate from this equation, that is R1 alpha delta T. This principle we can apply in a regular application in day-to-day life. There will be so many numerical examples based on this principle. What is that? Generally, when we observe a bullock cart, you will have a wooden wheel. The wooden wheel, generally it will be having some wooden spokes maintained like this. And now, encircling all these wooden spokes made like this, there will be an iron tire. There will be an iron tire placed like this. So you will have the normal wooden wheel like this, and you will have the iron tire which is tightly gripping it outside. Now practically, when the wooden wheel, suppose wooden wheel I want to prepare with a radius of 1 meter, and now the iron tire, you have to take the iron tire, and inside the iron tire the wooden wheel is to be placed, and it has to grip it very tightly. So that what we do is, when the wooden wheel is prepared with a radius of 1 meter, the iron tire which has to encircle the wooden wheel is made up of a radius only about 99 centimeter. Wooden wheel is of radius 1 meter and iron tire will have a radius only 99 centimeter. Then how it is possible to keep this wooden wheel inside the iron tire? At this condition it is not possible, because the radius of the iron tire is only 99 centimeter and the radius of the wooden wheel is 100. But now what we do? This iron tire is heated until the radius will be slightly greater than 100 centimeter. So that when it is heated, suppose the radius becomes 100.2 centimeter. Let us suppose, I am giving numericals only to understand the concept. I have heated the iron tire so that the radius becomes 100.2 centimeter. Very clearly now it is bigger than the wooden wheel. It is bigger than the wooden wheel. So when it is heated to higher temperature, the wooden wheel is placed at the center so that it will be exactly present inside the iron tire. And now because we have the wooden wheel present like this and we have the iron tire present outside, because slightly bigger than this, and now immediately we will pour lot of cold water on this iron tire. Then what happens? Iron tire is, because it heated to very high temperature, some hundreds of degrees of centigrade change in temperature, it is expanding to a length or to a radius of 100.2 centimeter. As a result, we are able to keep the wooden wheel inside. Now when we are pouring the cold water, what happens? Iron tire will cool down to the normal temperature, that is the room temperature. But when it cools the normal temperature, what happens? At the room temperature or normal temperature, its radius is only 99. So from this larger value of 100.2 centimeter at high temperature, it has to come back to the initial radius 99 centimeter while cooling to the room temperature. But already inside that we have a wooden wheel placed whose radius is 100 centimeter. So when the iron tire will try to contract to a radius of 99, the wooden wheel is there whose radius is 1 meter, that will be obstructing, so that the iron tire will be trying to come close to decrease the radius up to 99, but wooden wheel will be obstructing it, so that the iron tire will be tightly gripping the wooden wheel so that it will be fixed inside. So here what we are doing, we are heating the iron tire until this radius of this iron tire will be more than the radius of the wooden wheel. Then what is the mathematical condition required for this? Here in this example, as we have taken, wooden wheel has a radius of 100 centimeter. This is for wooden wheel. And for iron tire, the radius is only 99 centimeter we have taken. Then at least it must have a length of 100 centimeter. That means the final radius of this iron tire when you are heating, it must be 100 centimeter. So taking this as 100 centimeter, initial radius is 99, expansion is 1 centimeter. You can use the equation delta R equal to R alpha delta T. R alpha delta T, where initial radius is 99 and alpha we know the coefficient of linear expansion, and delta T we can find out the value of delta T, change in temperature, because delta R corresponds to change in the radius. So change in radius in this example is only 1 centimeter. So you can find out delta T from the equation delta R by R into alpha. So this is the change in temperature. You will get the change in temperature. But sometimes we may be missing a question, missing an answer also if you do not read the problem carefully. Because sometimes what he says is, initially the wooden iron tire is present at the room temperature 30 degrees centigrade. And when you substitute here the change in temperature, we got 250 degrees centigrade is the change in temperature. But remember, 250 is not our answer. This is only change in temperature. But initially it is at a temperature 30 degrees centigrade. From 30 degrees centigrade, it must be heated until the change in temperature becomes 250. which means that the final temperature that must be equal to initial temperature plus change in temperature. Clearly, if the initial temperature is 30 and final change in temperature must be 250, as per this equation, the final temperature must be equal to 280 degrees centigrade. So sometimes if we do not read the problem carefully, we may miss because we will be getting 250 as delta T, we may take it as an answer also. So remember, you have to listen or you have to study the problem very clearly. If the initial temperature is given, this is only change in temperature, we have to find out the final temperature up to which the iron tire must be heated so that it is exactly fitting the wooden wheel so that it will grip tightly. So this is an important application. Now let us move on to one more application. Let us discuss one more important application. What is that? Generally we use clocks to measure the time. The clocks we are using now, they are made up of digital clocks where simply a small electronic chip will give the time, which is very accurate. But in the olden days especially, they used pendulum clocks. These pendulum clocks, they are supposed to give correct time only at a particular temperature, because when the pendulum clock is executing oscillation, suppose let us take a pendulum. The pendulum clock, when it is oscillating between two extremes, depending on the motion of the pendulum, the hands of the clock, they will also be moving. The motion of the hands of the clock is coupled with motion of the pendulum. If the pendulum goes fast, the clock will also goes fast. If the pendulum goes slow, the clock also goes slow. So these pendulum clocks can give correct time at a only particular temperature, because if you take this length of this metallic rod, having the pendulum rod, suppose it is having a length L. When the temperature is changing delta L, there is an increase in the length or there is a decrease in the length. Let us say delta L equal to L alpha delta T. Corresponding to change in the length of the rods, length of the pendulum rod, what happens? For any type of pendulum, if you consider the time period, it is generally in case of simple pendulum we discuss, it is 2 pi root of L by G. This is not a case of a simple pendulum practically, but the relation between time and the length will be the same in all cases, where you can say that the time period of rotation is proportional to L power half. Then what happens? Suppose the time period of a pendulum is 2 seconds. Let us suppose. That means in 1 minute of time, because to complete one oscillation, it takes a time of 2 seconds. So in 1 minute of time, it has to complete 60 by 2, that is 30 number of oscillations. If it is exactly making 30 oscillations, let us suppose, to understand, let us have a numerical example like this. Then when it is exactly making 30 oscillations, the hands of the clock will be moving in a proper way so that we will get the correct time. Now this is happening only at a particular temperature, let us say some 20 degrees centigrade. Now suppose we are using this pendulum clock at a place where the temperature is very high. Then what happens? When because of high temperature, there is an increase in the length of the pendulum. But when length is increasing, time period will also be increasing. As a result, let us suppose that new time period, let us say T1 becomes 3 seconds. This much of change may not be there practically, but let us, I am taking this value to have an easy understanding. The time period now, because of increase of temperature, there is an increase in length. Because of increase in length, the time period is also increasing. Let us suppose that now the time period is 3 seconds. Now what happens? In the same type of 1 minute, it will complete only 60 by 3. That means only 20 oscillations. That means when it is giving correct time at a temperature 20, it is making 30 oscillations. Then hands of the clock will be moving in the correct way. You will get the correct time. But now in the same time in which it is expected to complete 30 oscillations, now it is making only 20 oscillations. Is it going slow or fast? Very clearly, in a time of making 30 oscillations, it is making only 20. So very clearly it is going slow. So these pendulum clocks will be going slow at high temperatures. Or we say in hot summer, the pendulum clocks will go slow, or they will be losing time. Going slow means if 1 hour is completed practically, the clock may show only some 58 minutes, 56 minutes like this. That means it is giving 4 minutes less amount of time. So that is possible at high temperature. Unlike this, if it is suppose we are using the pendulum clock at a lower temperature, at a place where the temperature is minus 20 degrees centigrade, corresponding to the fall of temperature, it will contract. When the length is decreasing because of contraction, the time period will also reduce. Now suppose the new time period, it has become only 1.5 second. That means in 1 minute of time, previously at a normal temperature, room temperature 20, it is making 30 oscillation. Now because of decrease of temperature, when you are using at a very low temperature, because of this change in length and time period, in the same time of 1 minute, it will be executing 60 by 1.5 or 40 oscillations. That means in a time of making 30 oscillation, now it is making 40 oscillations. Clearly it is going fast. So at low temperatures or in a severe winter, because of fall of temperature, pendulum clocks will be going fast, or we say it gain time. That means if 1 hour is completed practically, the clock may show some like 62 minutes or 63 minutes. It is adding some more time. So we say that it is going fast or it is gaining time. At high temperatures, it is losing time or going slow. And how much it will go fast or slow, that we will discuss in the next class. But for time being, remember that in hot summer at a high temperature, the pendulum clocks go slow, and at very low temperatures or at a severe winter conditions, the pendulum clocks will be going fast. So let us stop here. We will continue the next class.